Have you ever just stopped and wondered why we have so many programming languages? I mean, Python, C++, Java, Rust. Why not just pick one and stick with it? What really makes one language the perfect tool for a job while another one just isn't? Well, today we're going to pull back the curtain and look at the design, the philosophy, and the pure engineering that goes into the code we write every day. Okay, let's get into it.
So here's our roadmap. First, we'll talk about why studying this stuff even matters. Then, we'll try to pin down what makes a language good in the first place. After that, we'll see why there's a different tool for every job, and we'll look under the hood to see how our computers actually understand any of this. And finally, we'll wrap it all up with the key blueprints you can use to write better code.
All right, so section 1, why even bother with the theory? It's a totally fair question. You could just learn the syntax of one language and be done with it, right? Well, the thing is, understanding these core principles makes you a fundamentally better problem solver. It's the difference between just writing code and actually engineering a solution. When you really get these concepts, your whole approach changes. You're not just thinking in one language anymore. You're able to express your ideas more clearly and powerfully. You suddenly have this background knowledge that helps you pick the right language for the project, not just the one you know best. And you know what? Learning new languages becomes way, way easier because you see the patterns. It's like having a master key to unlock any new syntax that comes your way. Okay, that brings us to the next big question. What actually makes a programming language good? And spoiler alert, it's not just about which one runs the fastest. Language designers are constantly juggling a few key criteria to build the tools that we get to use. So, believe it or not, the absolute #1 most important criterion is readability. Just think about it for a second. Code is read so much more often than it's written. Whether it's your teammate trying to understand your logic, or you, 6 months from now, trying to remember what you were thinking. If the code is hard to read, it's going to be a nightmare to maintain and debug. Clarity is king. And this is a perfect, simple example of that. On the left, timeout equals 1. What does 1 even mean? Does it mean true? Does it mean 1 second? Who knows? But on the right, in a language that supports a proper Boolean type, timeout equals true, is crystal clear. There is zero ambiguity. The code explains itself. And that right there prevents a whole class of bugs. Another thing that messes with readability is this idea of multiplicity. Here you see 3 different ways to do the exact same thing. Add 1 to a variable. Now, for a seasoned pro, count++ is short, sweet, and to the point. But for a beginner, it can be pretty confusing. So language designers have to strike this tricky balance. Do they give you lots of powerful shortcuts, or do they keep things simple and explicit to make the language easier to read? Now, closely tied to readability is writability, and that's all about how easily you can translate your ideas into code. It's about how naturally the language lets you express a solution. This is where features like abstraction come in, letting you build big, complex ideas out of smaller, simpler ones without getting bogged down in the tiny details. To really dig into writability, we have to talk about syntax. It's really simple. Just like English has grammar that tells us how to build a proper sentence, a programming language has syntax. It's the set of rules that define what a valid, understandable instruction looks like. It's the basic structure of the language. But how do you describe those rules without any room for error? How do you write down the grammar of a language so precisely that a computer can understand it perfectly? Well, you use something called a metalanguage, which is, and this is cool, a language used to describe another language. The most common one is called back-as-nar form, or BNF for short. Let's look at a super simple example. This is a BNF rule that defines an assignment statement. See the assign on the left? That's what we're defining. The arrow basically means is defined as. And what is it defined as? A variable, var, followed by an equal sign, followed by an expression. It's a formal, unambiguous blueprint for one of the most common pieces of code we write. This whole idea of blueprints and having the right tools for the job is exactly why we have so many languages. You wouldn't use a hammer to saw a piece of wood, right? In the same way, different types of programming problems require completely different tools, and languages have evolved to become those specialized tools. If we look back, we can see these big categories or domains that really drove the creation of new languages. You had scientific computing, business applications, artificial intelligence, systems programming. Each of these worlds had its own unique set of challenges that demanded a new way of thinking. For scientific apps, the name of the game was raw number crunching speed. You needed to do incredibly complex math, and you needed it to be fast and accurate. This is where a language like Fortran came in. Its name literally stands for Formula Translating System. It was built from the ground up to be a beast at handling huge arrays and matrices for things like weather prediction or physics simulation. Now, on the complete opposite end of the spectrum, you had business applications. They didn't care about fancy math. They needed to process massive amounts of records. Think payroll, inventory, and bank transactions, and generate reports. So COBOL was born. It was designed to handle decimal arithmetic perfectly for money and to make managing and reporting on data as straightforward as possible.
And then you get to a domain that's totally different from either of those: artificial intelligence. AI research wasn't about crunching numbers or processing records. It was about manipulating symbols and ideas. This led to fascinating languages like Lisp, which stands for list processing. Its most basic data structure was the list, which is just a perfect way to represent abstract concepts, logical rules, and even code itself.
So we've got all these specialized, human-friendly languages. But how does a piece of silicon, a CPU, actually understand any of it? How does a simple line like print hello actually make pixels light up on a screen? Well, that brings us down to the level of implementation. You know, the design of pretty much every computer we use today is based on what's called the von Neumann architecture. The really big idea here is that the program's instructions and the data for that program are all stored together in the same memory. And the CPU is a separate unit that has to fetch everything from that memory. This basic design is the reason why imperative languages like C work the way they do. Variables are like little boxes in memory, and assignment statements are like moving data into those boxes. And at the very heart of that CPU is this simple, relentless loop, the fetch-execute cycle. It's the heartbeat of the computer. It just fetches an instruction from memory, figures out what it's supposed to do, does it, and then moves on to the next one. Billions of times per second. This little dance is what brings all of our software to life. But this architecture has one famous weakness: the von Neumann bottleneck. Think of that connection between the super fast CPU and the slower memory as a small pipe. The CPU is thirsty for data and instructions, but it can only get them through this one relatively slow pipe. This bottleneck, the speed of that connection, is often the main thing limiting how fast our computers can truly go. So, to bridge the gap between our code and that fetch-execute cycle, there are two main strategies. Compilation is where you translate the entire program into low-level machine code all at once, before you run it. It's fast to execute, but the translation step is complex. Then there's interpretation, where a program reads your code line by line and executes it on the fly. It's more flexible, but a lot slower. The cool thing is, most modern languages like Python and Java use a clever hybrid approach to get the best of both worlds. Phew. Okay, we've gone on quite a journey, right? From the high-level philosophy of language design all the way down to the bare metal of how a CPU works. So let's bring it all together and talk about the key blueprints you should take away from all this. So, what's the big picture? First, knowing the why behind language design helps you express your own ideas so much better. Second, a good language isn't about some objective measure. It's about the right balance of readability, writability, and reliability for the specific task at hand. Third, we saw that history isn't random. Specialized problems in science, business, and AI directly led to the specialized languages we have. And finally, never forget that all this beautiful abstract software is built on the physical reality of a computer's architecture. And that brings me to one last thought to leave you with. The world is always throwing new problems at us, from managing planet-scale data to programming quantum computers. The evolution of language isn't over. So with all these principles in mind, I'll ask you this. If you could create a brand new programming language today, what massive unsolved problem would you design it to conquer?